Considering the limit examples in the previous video, we established that if you're dealing with a polynomial function or a rational function, really the easiest way to determine the limit is to try and evaluate the function given the limit value that you're approaching. So what we can say, consider a limit of a polynomial, or say we are given a polynomial function, we'll call it p of x, equals a sub n, x to the n, plus a whole bunch of terms all the way down to a sub 0 constant term. Okay? If we have some polynomial, then the limit as x approaches some number c for that polynomial function, that is going to equal the polynomial evaluated at c, or p of c. So if we're given the limit of something that's a polynomial, we just want to evaluate the polynomial at that x value we are looking to approach. And if we're dealing with a rational function, remember a rational function, some r of x function, is just a ratio of two polynomial functions. Okay, so if we want to find the limit of some rational function as x approaches c, again, all we would do would be evaluate that function, because a rational function behaves very much like a polynomial function, considering it is a quotient or two polynomials divided. Right? It's a quotient of polynomials. So all we need to do is evaluate it. But we have to add one small piece here, and we have to say this works as long as q of c, whatever number we get in the denominator, isn't equal to 0, right? So this works as long as we don't have 0 in the denominator. So recapping those two rules, if you have a polynomial function or a rational function and you're asked to find the limit, just plug the value in. So let's look at two examples. So here we have a rational function. We are looking at the limit as x approaches -1 of the rational function created by the quotient, or dividing two polynomials. We have a cubic polynomial, x cubed, in the numerator over a quadratic polynomial in the denominator. So x cubed plus 4x squared minus 3 divided by x squared plus 5. If we want to find the limit, all we're going to do is plug in -1. And the only reason this wouldn't work would be if I wound up with 0 in the denominator. So let's look at this. I've got -1 quantity cubed plus 4 times -1 squared minus 3 over -1 squared plus 5. If I simplify the numerator, I have -1 plus 4 minus 3 gives me 0. And in the denominator, I get 6. 0 divided by 6 is 0. That is the limit of this rational function. So let's look at another example. Find the limit. And I'm going to present this one a little bit differently. Say we are given p of x equals x squared minus 10. And I might ask you and say find the limit as x goes to 1 of p of x. So in this situation, that means the same as finding the limit as x goes to 1 of x squared minus 10, which would be 1 squared minus 10, or -9. So the limit as x goes to +1 of x squared minus 10 is -9. And just to help us connect what we're thinking about, if I were to graph my polynomial function, in this situation, graphing that polynomial, it would be a parabola opening up, shifted down 10 units. So we'd have a vertex here at 0, -10. And we would also have this point on the graph positive 1, negative 9. So the function value tends towards or goes to negative 9 as x approaches 1. So what occurs when you plug the value in and you end up with 0 in the denominator? So let's look at this. Here, we're going to say we're going to find the limit as x approaches negative 1 of x squared minus 1 over x plus 1. And a quick analysis of this problem would let me know if I plug negative 1 in, I'm going to end up with a 0 value in the denominator, which we know is not okay. So the first thing we do when we're trying to figure that out would be to try and factor it. And in this case, the limit as x goes to negative 1, this numerator can be x minus 1, x plus 1. It factors as a difference of squares over x plus 1. We see that we can cancel a common factor. And doing that leaves us with determining the limit as x approaches negative 1 for x minus 1. And this, of course, is a linear polynomial. So here we would take that negative 1 value and we would just plug it into the function, negative 1 minus 1. Notice once I go to that step where I'm plugging it in, I no longer need to write limit. In this situation, the solution is negative 2. So let's look at that graph. If we were to graph this in our calculator or by hand, we would get a line with a y-intercept at negative 1 and a slope of positive 1. So if I were to graph this, just plot a couple points there, we would have that y-intercept. We would also know that if I plug negative 2 in, I would get out negative 3. Or if I were to plug positive 1 in, I would get out 0. So here we see that line forming. But what we want to notice is the graph will have a hole. Okay? So we're going to have a hole at negative 1, negative 2. So what that leads us towards this idea of a limit. As x is approaching, as x is getting closer and closer and closer to negative 1 from both the left and the right, where does my y value go? And it's approaching negative 2, right? So we're getting infinitely close to that x equals negative 1 value, but never touching it. And as we get closer and closer and closer to x equals negative 1, we'll get a value that's closer and closer and closer to y equals negative 2. So the main thing here, when we are dealing with a rational function and we plug in x equals whichever number we are approaching and we get 0 in the denominator, we try to figure out a way to manipulate the function so that that 0 goes away. And as we work through these problems, we're going to notice a lot of the times I'm going to give you limit problems and you're not just going to be able to plug the number in, because where would be the fun in that, right? I don't want you to just plug it in and tell me what the output is. I want you to say, okay, well, I tried to plug this number in and my output didn't work. How can I manipulate it to figure out what number we are approaching? So let's look at 2 more examples. Let's look at eliminating common factors from 0 denominators. We'll do 2 examples. The limit as x approaches 0 of x squared minus x over x. In this case, this is the same as writing the limit as x approaches 0 of x squared over x minus x over x. When I have one term in the denominator, I can unadd, in a sense, and simplify each of those smaller fractions. So this is the limit as x approaches 0, x squared over x is x, and x over x is 1. At this point, I take the value I'm interested in approaching, x equals 0, and I plug that in for x. 0 minus 1, that gives me negative 1. And I want you to notice, once I plug that value in, I no longer am writing limit. I'm evaluating it at this point. So my answer was negative 1. Let's just look at one more. We'll say the limit as x approaches 2, 3x squared minus 5x minus 2 divided by x minus 2. So I have a quadratic polynomial over a linear polynomial. And the nice thing here is this quadratic polynomial factors. Now, I would look at this when I'm trying to factor my numerator and say, well, there's probably an x minus 2 in there. I mean, the reason I'm thinking that is because I have x minus 2 in my original denominator. But that's not always the case. So don't let some of these problems trick you. What we're trying to do is, figure out how to factor this so that something will cancel. So I'm hoping that the x minus 2 is in there. And in this case, when I factor it, that leaves me with 3x plus 1. So it does show up in there. It factors nicely. I'll cancel those common factors. That means I'm now solving the problem to determine the limit as x approaches 2 of 3x plus 1. So now I'm going to take my 2 value and plug it in. That gives me 3 times 2 plus 1, which is 7. So 7 is the answer to this limit problem.